So our next speaker is Professor Onur Mutlu. He is the professor of computer science at ETH Zurich. He's also a faculty member at Carnegie Mellon University, where he has held the Strecker Early Career Professorship. And his research interests include computer architecture, systems, hardware security, and bioinformatics. And today he'll be talking about the story of RowHammer. So Onur, please go ahead and share your screen.
Okay, thank you, Priya, for the introduction. Let me share my screen. Okay, can you see it?
Yes.
Okay, great. Okay, now I can see it also. I'm going to talk about RowHammer in this talk, including the fundamentals as well as some recent research. I have a lot of slides. It's a high bandwidth talk, but I'll try to skip a lot of slides also. I'll make these slides available to anybody who wants it. So what is RowHammer? Basically, it's the fact that you can predictably induce bit flips in commodity DRAM chips today, and many chips are vulnerable. They were vulnerable in 2012, and they're still vulnerable today. What's interesting about this is that this, I believe, is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And as a result, people are writing articles that look like this. Forget software, now hackers are exploiting physics. And clearly, we knew a lot about memory technology scaling for a while. This is one of the summary papers that we wrote about 8 years ago. And especially DRAM has not been scaling very well. Dynamic random access memory technology, as we reduce the size of a DRAM cell, its reliability certainly reduces due to issues in the capacitor, access transistor, as well as the sense amplifiers. And we know that you get more errors in DRAM chips, especially based on the large scale studies that people have done, including us with Facebook in this particular case. As the chip density that's employed in a data center increases, you get higher server failure rates because chips are more vulnerable to reliability issues. And if you're interested, there's a lot of data in the field. But we really wanted to understand these reliability problems by doing small scale experiments using FPGAs. And that's why we built some infrastructures that look like this. For example, these are FPGA-based memory testing infrastructures. And we open sourced it in 2017. Anybody can use it. People are actually using it in industry as well as academia to do very interesting studies, and we'll be very supportive of that. And you can find it over here. While we were doing a lot of studies with these infrastructures together with Intel, we found out that basically you can predictably induce errors in most DRAM memory chips. And that's the DRAM RowHammer phenomenon that I mentioned about. So what happens exactly in RowHammer? You have multiple rows in DRAM. And if you repeatedly access one row, meaning apply high voltage to that row and then apply low voltage, this is called activate precharge in DRAM, activate precharge, activate precharge, activate precharge, essentially access one row. It turns out physically adjacent rows get bit flips. We call this a hammer row, we call this a victim row, and clearly this should not happen, right? You, based on memory isolation principles, whenever you read from memory, you should not modify any data, including your own data, but now you're modifying some other data that may potentially belong to someone else. And this is a widespread industry problem. Basically, this did not occur in chips that were manufactured before 2010, and the first appearance is in 2010. And all chips that we tested that were manufactured between 2012 and 2013 were actually vulnerable to this effect. So this is a scaling problem, technology scaling problem, because at some point cells became too small and too close to each other. As a result, the electromagnetic interference is affecting cells that are close to each other. And what is worse about this is now a simple program can induce many errors. You can write an assembly program like this. This is what we released when we actually wrote our paper. And what this program does is basically it accesses rows X and Y in a single DRAM bank. And if the chip is vulnerable, hopefully you'll get bit flips. This is not the worst program you can write. You can actually write much worse programs, as later folks showed. But our proof of concept at the time showed that this is a real reliability and security issue. And we demonstrate this on Intel and AMD systems. And essentially, if you can write such a program, you can also take over a system because you're breaking memory isolation right now. And Google Project Zero folks were the first to show that you can do this on a real system, taking over x86 64 Linux. I'm not going to go through the slide, but this is essentially copy and pasted from their blog post, Google Project Zero's blog post. What they did was they were able to replicate the RowHammer problem and induce bit flips and page table entries. And as a result, as a user level process, they could gain write access to the page table of that process. And once you gain write access to your own page table, you can actually circumvent any type of protection on the system. And as a result, people actually are were making jokes like this. These are famous hackers, actually. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I kind of like this analogy. There are a lot of actually interesting attacks that were developed due to this RowHammer software-inducible bit flips. I'm not going to go into the details since we don't have time, but you can see a lot of very interesting papers published at top security venues, taking over different kinds of systems, even through remote direct memory access, or leaking data, breaking confidentiality, for example. Even if you cannot actually take over the system, you may actually break confidentiality and actually leak data from the system. And more recently, we've been seeing some papers that show that neural networks, if you actually target these bit flips through RowHammer, an otherwise perfectly accurate or reasonably accurate neural network may lose its accuracy completely because you get these bit flips. And there may be other interesting attacks, for example. So if you're interested in a lot of this, we cover in this survey paper a lot of issues related to RowHammer across the stack. But keep in mind that this is from 2019. Now, let me quickly mention, understanding RowHammer is important actually to build real systems. And that's what we did in our first RowHammer analysis paper. That's what we have been doing by building new infrastructures. And initially, we tested 129 models. You will see more recent results soon. And again, I'm not going to bore you with the analysis, but there's a lot of interesting analysis about the RowHammer phenomenon. And you can find that in this paper. And more recently, we've shown that RowHammer is getting much worse. And I'm going to talk about this briefly later in the talk. And more recently, even more recently, we showed that RowHammer is actually getting even worse than we thought because it has many, many dimensions. I will mention this also in a little bit. But before I mention those recent studies, let me talk about RowHammer solutions a little bit. What kind of solutions do we want? First of all, clearly, some chips in the field are vulnerable. So we need to immediately protect them. And there are limited possibilities we have. Increasing the refresh rate is one. Longer term solutions need to be more fundamental, I believe. And we should come up with a wider range of protection mechanisms. And in our original paper, we propose multiple solutions. And I will describe one solution that I still believe is interesting, but it needs to be augmented today. So these are some solutions that I don't believe work extremely well because they come up with high cost, high power, high performance, etc., and complexity. Especially making better DRAM chips is difficult because isolating cells have been proven difficult. And refreshing frequently, although that's been employed, is not a great solution because it clearly increased the energy consumption and performance overhead. I'm not going to talk about the details. You can find that in our survey paper. So what the industry employed in existing systems is increasing the refresh rate because that's the simplest thing to do. And that's the configurability you have in your memory controllers today. That's a bit unfortunate because our memory controllers don't allow us to patch things or make things, essentially patch things so that you can prevent issues like this by executing programs or executing code potentially. So our solution, our proposed solution require changes to the memory controller or the DRAM chip. And the idea is very simple, probabilistically activate adjacent rows. After you close a row, with very little probability, activate adjacent rows, neighbors. And if you do that, you essentially refresh the data before, and you actually get rid of the hammering effect by refreshing the data quickly before the charge gets lost. And as a result, you get significant reliability guarantees, which you can adjust with a user configurable parameter. And this is a nice solution. It requires to be reinvestigated even more, in my opinion, to actually be much more scalable going into the future. We'll talk about that in a little bit. But you can implement solutions in the DRAM chip or in the memory controller. This kind of solution can be implemented in both places. It was actually done by Intel in the memory controller with some caveats. Today, versions of it are implemented in the DRAM chip, but we will talk about the caveats of that also because they're not necessarily implemented in a secure manner. And this is an example of the solution that was that was done by Intel at the BIOS level. And again, for details, you can read the papers that I mentioned, including this one. So takeaway, I think if you really want to solve this sort of scaling problems, we need intelligent controllers to enable better scaling, security, safety, and reliability, because RowHammer is in the end such a problem. And I think we know how to build intelligent controllers, except for other memory technologies. This is NAND flash, for example, and we know exactly how to build these memory controllers for slower memory technologies. Now we need to figure out how to do that with much faster memory technologies like DRAM. So if you're interested in RowHammer, there's a lot more analysis I mentioned. I'll quickly now go into what has happened recently in 2020 and 2022, because a lot of interesting things happened in RowHammer. First of all, as I said, we revisited RowHammer. We wanted to understand its scaling. And we did a large-scale testing study of more than 1,500 DRAM chips. And we found that essentially that newer DRAM chips are much more vulnerable to RowHammer. You get more bit flips that happen earlier. In fact, there are some chips whose weakest cells fail after only 4,800 double-sided hammers. This is a very low number. And unfortunately, existing mitigation mechanisms are not affected at future technology nodes. They may work at higher technology nodes, but as the technology scales, they become very ineffective, meaning either they don't work or they have very high overhead. So they're not scalable. So that's just one example, basically. Newer chips are a lot more vulnerable, as you can see, compared to the older chips in this study. And bit flip rates increase with technology node generation. This is another example. Newer chips from each DRAM manufacturer are found to be more vulnerable to RowHammer. I'm going through this relatively quickly because we don't have a lot of time, but you can find a lot of details on the papers. And you can also find a lot of lectures. Let me talk about the trespass issue. Here, we wanted to understand basically whether industry adopted solutions work. Industry basically said, DRAM industry basically said, we solved the problem, trust us. And of course, as a researchers, we should not really take this as a given. So what we did was we basically tested that. And we showed that TRR protected, target row refresh protected DRAM chips are vulnerable to RowHammer in the field. Mitigations that are advertised as secure are not secure. And this introduced a many-sided RowHammer attack. By hammering many rows to bypass TRR mitigations, industry internal mitigations in DRAM, you can overflow proprietary TRR tables that detect aggressor rows, essentially. And we did that by partially reverse engineering these mitigation mechanisms. And we also provide an automatic tool that can effectively create many-sided RowHammer attacks that anybody can use. And in fact, people have been using that. So many-sided attacks are basically hammering more than 2 rows. That's the idea. And you basically get bit flips in protected chips, advertised as completely secure against RowHammer, after you hammer more than, let's say, 5 rows, 7 rows, 10 rows, and in some cases 19 rows, actually, yes, 19 rows. And this actually, you can actually take over mobile phones that are vulnerable this way. And attacks are actually really fast, as you can see over here, and you can read the details in the paper. So basically, this was a proof of concept that shows that real chips that are actually implementing protections are vulnerable, and mobile phones are vulnerable. And these results are were scratching the surface because our tool was not exhaustive and there was a lot of room for uncovering more vulnerable chips. Clearly, RowHammer is still an open problem, and security by obscurity is likely not a good solution. To solve the problem, we really need better security mechanisms implemented in industry. Okay, so we also wanted to ask the question, how do you guarantee that a chip is RowHammer free? Unfortunately, there's no good answer to this. I don't think that you can guarantee that at this point. We don't have a good methodology to do that. I'm not going to talk about this, but you can find information in this paper. Later, we said that, oh, can we uncover these TRR mechanisms that were adopted by industry completely? And we almost succeeded that. I'm not going to say completely. We really succeeded almost completely. And the idea is to use this new methodology that leverages data retention failures to uncover the inner workings of TRR and study security. We basically developed this methodology that enables us to craft new RowHammer access patterns. And as a result, we can actually circumvent all modules we tested. We can see a lot of vulnerability in real chips, and ECC is completely ineffective. Okay, so this can hopefully facilitate, this work can hopefully facilitate more secure RowHammer protection mechanisms. The key idea is really used to data retention failures as a side channel to detect when a row is refreshed internally by the DRAM chip. So the DRAM chip is doing internal refreshes to prevent RowHammer, and you can actually find out information about that because there's a side channel created. And we did real studies from 45 chips over here. You can find a lot more information in this paper. And I'm going to skip these because this has basically overall more information. And there's a lot more information than I described also in the paper. New RowHammer characteristics are also interesting to study. And this is a recent study from Micro 2021 that we did. We wanted to understand 3 fundamental properties and their effect on RowHammer: temperature, how long the aggressor row is active, and physical location of the DRAM cell that you're targeting. What is the variation of physical location? And we basically developed an understanding, again, using experimental studies. This is our latest infrastructure, actually, with DDR3 as well as DDR4 based. And we did studies on 4 different manufacturers in this particular case. And basically, we found out that a RowHammer bit flip is more likely to occur in a bounded range of temperature, which depends on the chip, if the aggressor row is active for a longer time, and in certain physical regions of the DRAM module under attack. So if you target certain physical regions, you can actually be more successful. You can use this to create more effective attacks, as well as more effective defenses. And that's what we did. For example, by understanding the aggressor of active time, a better attack can reduce the minimum activation count to induce a bit flip by 36% and can bypass defenses, sorry about that, that do not account for this reduction. And also, you can improve the defenses by making them more efficient because you don't have to protect the entire DRAM chip at the same level of aggressiveness. And there are more analyses in the paper, but I do not have time to talk about that. Let me talk about new RowHammer solutions because this is a very important direction. There's a paper in ASPLOS 2022 that's coming also on this. There are 4 major mitigation approaches: increasing the refresh rate, physical isolation, reactive refresh, and proactive throttling. And these approaches have many key challenges, but two important key challenges are how do you make things scale with worsening RowHammer vulnerability into the future? And how do you become more compatible with commodity DRAM chips? Ideally, you don't change anything in the DRAM chip from a memory controller perspective. And our goal was to actually achieve both of them. And the key idea in this work is to selectively throttle memory accesses that may cause RowHammer bit flips. I will not go through the details of the approach. Just implement the memory control. It's an intelligent memory controller approach. I will let you read the paper if you're interested. But basically, this approach is competitive with state-of-the-art mechanisms when there's no attack and superior performance energy. And it can, with very high probability, detect a RowHammer attack. And you can kick it out from your system or do more analysis, if you will. And enables better hardware area scaling with RowHammer vulnerability while having a security proof. And we study 14 mechanisms representing 4 mitigation approaches in this work. And you can see that analysis. I believe going forward, we need to have more rigorous analyses of RowHammer defenses into the future. So basically, the takeaway, in my opinion, is that main memory needs intelligent controllers for security, safety, reliability, and scaling. That controller may be implemented inside the memory chip or outside the memory chip, but I think we need to do more. So there's a lot more work that I did not cover. You can find more information about these papers. This is from 2021. 2022, actually, this is the paper I mentioned at ASPLOS 2022 that's coming up. I believe there's more to come. I'm going to skip this part about future challenges. There are other technologies that are also challenging. Sorry about this. But I think, again, intelligent memory controllers can avoid the failures and enable better scaling. So let me give you some final thoughts. This is a very paper that I really like, actually. It's from IEEE Security and Privacy from 2003. It was written ahead of its time, maybe. These folks actually used memory errors to attack a virtual machine, take over a virtual machine, basically, bit flips. The way they induced bit flips is by heating the memory on this machine. This is before RowHammer. I think this paper needs to be given more credit, frankly. But after RowHammer, those bit flips, you don't need physical access to the machine. A simple memory error can be induced by software because of RowHammer. So I believe RowHammer enabled a renewed interest in hardware security attack research. Real memory chips are really vulnerable through software, and hardware reliability and security connection is now mainstream discourse. There are many new RowHammer attacks. I believe they will keep coming. Many new RowHammer solutions. I believe they should keep coming so that we can actually be safe and secure. And basically, I think RowHammer is proof that general purpose hardware is fallible. I think we really need to examine other general purpose hardware as well. And this is happening, I think, at a scale. Google and Facebook both published papers on silent data corruption. More recently, in 2021, actually, there's a HotOS paper by Google on chips that do not work, for example. Okay, I'm going to skip this one and conclude, basically. So takeaway, I think, is memory reliability is reducing. Reliability issues open up security vulnerabilities, also safety vulnerabilities. These are very hard to defend against. RowHammer is a prime example. And as I said, this is the first example that I know of a simple hardware failure mechanism that can create a widespread system security vulnerability. And I believe its implications on system security research and defenses are tremendous and exciting. The bad news is RowHammer is clearly getting worse. And good news is we have a lot more to do in all parts of the industry and academia. We are fully aware that hardware is easily fallible. We're developing both attacks and solutions, and hopefully principled models, methodologies, and solutions to fix the problem. And again, if you really want more, the survey is a 2-year old survey that talks about a lot of these issues that I mentioned. Then you can find more information online. I will thank people for funding us and definitely thank my research group for actually being part of this research over the course of 8 years. And these are them. Thank you very much. I'm happy to have any questions.
Thank you so much, Professor Mutlu. That was really a very informative and a packed talk. So we do have some time for questions. So if there is any question from the audience, please feel free to unmute yourself and pose a question. Maybe like I can start off like, so I was just wondering, and you, I think, pointed briefly around it that, you know, technology scaling is not helping with RowHammer attacks. And maybe you showed a perspective of DRAM, but, you know, as new technology is coming in terms of embedded memories. So what do you think is like, you know, do we always come up with this, like, you know, every time we come up with a solution and then we attack it? Or is there a way to universally approach some kind of a robust, you know, from a technology side or from an architectural system? So what is your perspective on how to develop a more robust end-to-end scheme for such kind of hardware security vulnerability?
That's a great question. Those are some of the slides that I skipped in terms of future memory security reliability challenges. Clearly, DRAM is a very important technology, and any error exposed in DRAM is directly exposed to the programming language data structures, right? That's why RowHammer is very, very interesting. But yes, I agree. There are other memory technologies that also have similar problems. Some papers have demonstrated that usually in simulation. sometimes in real chips also. I believe if we understand the solution really well, then we can develop fundamental techniques across memory technologies. Even though different memory technologies have some differences, I think moving data, refreshing rows, we can develop general solution classes. But I think it really comes down to understanding the solution, understanding the problem really well with using these studies and developing these architectural methods that can solve the problem in different design points, because different memories are also in different points in their development. They may not need as much protection, but you may have some configurable protection mechanisms like refreshing, probabilistic adjacent row activation is one example, RowHammer is another example, that you can adapt to different memory technologies. So I believe, short answer to your question is yes, I think we can find fundamental solutions, but we need to somehow configure them to different memory technologies to be really efficient in a given setting.
Got it. Thank you so much. Are there any other questions? Okay, if not, thank you so much, Professor Mutlu. That was a wonderful talk. And please stay back. If there are any questions, please answer them on the chat. And definitely all of the slides as well as the talk will be available for later viewing as well.
Okay, thank you very much.
Thank you.